Welcome to PowerFactory 2019. As always, we continue to develop PowerFactory to meet customer needs in the ever-changing world of electricity supply and demand. In this video, I will demonstrate some of the new functions that we have introduced in this release, together with a few of the other features and enhancements that we hope you will find useful and interesting. I will start by showing you the new Unit Commitment and Dispatch Optimization module, designed to integrate market data into the network model and use this for optimizing generation dispatch over a period of time. The new module combines the optimal power flow calculation algorithm with quasi-dynamic simulation and is accessed via the Optimal Power Flow Unit Commitment toolbar. The optimization can be based on either AC or DC load flow, and in this example will be run at hourly steps over a period of 2 days. On this page, the objective function is selected. The default is to minimize total costs, but the user can instead select individual cost components to be minimized. Within the generator elements, the various costs are set up on the unit commitment page. Operating costs may be specified locally or via separately defined cost curves. In this project, generic cost curves for each fuel type have been used. Additional redispatch costs may be defined, as well as startup and shutdown costs. And ramp rates and minimum on and off times may be entered here. Returning to the command dialog, on this page the controls and constraints are defined. We will use just active power dispatch as a control. On the algorithm page, the user can select one of the 2 inbuilt solvers, but there is also the possibility to make use of an external linear programming solver to make the calculation much faster. The calculation can now be executed. Statistical results can be viewed in a flexible data page or on a graphic, and results quantities across the time period are also available and can be visualized using plots. These plots show the active power for the different fuel types, and the 2 plots show the generation as it would be using a simple quasi-dynamic simulation, and then as it is after the redispatch by the unit commitment optimization. We see that the nuclear generation is now running close to its maximum, and the gas and coal generation is reduced. Now let us consider a scenario where emission charges have been significantly increased. As coal has a higher emission intensity than gas, emission costs are more onerous for coal, and so we expect this to be reflected in the redispatch of the 2 fuel types. With the calculation executed again, we can see in the lower graph that this time there is significantly more gas generation compared with coal. Inbuilt reports are also available, such as this generation summary report. There is an additional option to consider planned outages. In this case, we have just one planned outage for 2 hours on the generator transformer of one of the nuclear generators. The calculation is executed again. The plots here illustrate what happens. The first plot shows how the generator off time is extended because of the minimum downtime parameter of the generator. The placing of this outage period is optimized for cost. The remaining 2 plots show how the ramp rates for the outage generator are taken into account, and the increased output of one of the gas-fired generators can be seen. We can use diagram colouring to see immediately whereabouts in the network the redispatch costs are incurred. These are the costs associated with the generation changes compared with the default quasi-dynamic simulation, which have been made in order to minimize the overall costs. Co-simulation is an extension to the existing EMT and RMS simulation calculations. It enables the user to analyze two or more parts of a network simultaneously. This not only offers benefits in terms of speed, but also enables simulations in different domains to be executed concurrently. In this project, the network is divided into two regions. Although only connected via two circuits, there is an interaction between the two that should not be ignored during simulations. Let's start first with a normal, sequential EMT simulation of the whole network, with a fault being applied at this terminal. Here we can see the fault being applied and cleared after 100 milliseconds. Let us now look at the options for co-simulation. Single-domain co-simulation will generally be used for large networks to achieve faster simulation runtimes, as it makes use of multiple cores on the user's machine to carry out the simulations in parallel. The initial condition options are configured here. EMT analysis has been selected. On this page, the regions are shown, the interfaces between them being defined using boundaries. The calculation of initial conditions is executed. Then the simulation itself is run. In this example, as an EMT simulation is run, we can see the instantaneous currents at the boundary for both regions. The multiple domain simulation functionality allows the user to combine simulations in different domains, namely EMT, RMS balanced and RMS unbalanced calculations. The benefit of this is that the user can carry out a detailed EMT simulation of one part of the network and just consider the rest of the network in the RMS domain. For multiple domain simulations, the two separate setting configurations are accessed here. In this example, we will execute an RMS unbalanced simulation in region 1 and an EMT simulation in region 2. This time we can see the magnitude of the boundary currents for region 1 where the RMS simulation has been executed, and the instantaneous currents from the EMT calculation for region 2. There is also a separate option for co-simulation with an external solver, which enables co-simulations to be executed using multiple PowerFactory instances or between PowerFactory and a third-party simulation tool. For the analysis of distribution networks in particular, the new hosting capacity tool calculates the amount of generation or consumption that can be connected to the grid without any network expansion, whilst not violating any system constraints. Hosting capacity analysis is accessed via the Distribution Network Tools toolbar. The calculation objective must be selected: distributed energy resource, i.e. generation, or spare load capacity, and the system type is specified. Then the relevant constraints are selected here. On the Constraints page, the constraints are configured in detail. For example, when considering protection devices, the user might select to prohibit reverse power flow. And power quality limits are taken into account using harmonic load flow analysis. Here, one or more hosting sites is selected, which may be individual terminals or grouping objects such as feeders or zones. In this case, we have selected just one feeder, which means that all terminals along the feeder will be considered as hosting sites. That is, the capacity for additional generation to be connected, whilst maintaining network security within the prescribed limits, is calculated for each terminal along the feeder. In this project, the calculation has already been executed, so I will simply use the Reload of Results option to reload the results back into memory. The results of the analysis can be viewed in dedicated reports. In this report, it can be seen that the limiting factor is branch element loading, and the effect of the additional generation can be visualized by generating a heat map. The colouring indicates how the capacity for hosting additional generation changes along the feeder. The analysis has also been carried out for all feeders on the network, and the results can similarly be loaded and viewed in a single line diagram or on a geographic diagram. I would now like to show you a couple of other enhancements to existing analysis functions. For contingency analysis, a new calculation method is available. This linearized calculation method is much faster than the more accurate iterative AC method, and so can provide a useful starting point for the analysis of large numbers of contingencies. Another feature that has been introduced into contingency analysis, as well as other calculation functions, is the reloading of results into memory. Staying with contingency analysis, we can look at how this is used. At the moment, as I have just run the calculation, we can see the summary results such as maximum loadings in a network model manager. Now I will reset the results. In this situation, we have the new option to load the results back into memory. I can simply execute the command and we see the results again. Note that a grey colour is used to indicate that the results are being reloaded. This is an important reminder to the user because it is possible that the network has been changed since the calculation was run, and therefore the results may no longer correspond to the current network state. Another very useful aspect is that one can load just the results for a particular contingency. This makes it possible to look at the results for various contingencies in a network model manager or on the graphic, without having to recalculate them individually. As I indicated earlier, this reloading of results option is not restricted to contingency calculations, but is now included in a number of analysis modules, such as quasi-dynamic simulation, where it can be useful for the situation where results have become reset after a lengthy simulation. In this section, I will show you some of the graphical features that we have introduced in this version, starting with the updated layers concept. The project that I'm using has been created by combining our standard MV distribution and transmission examples using our project combination tool. On the geographic diagram, the transmission network is currently shown, but the MV network elements have been placed in a separate layer which at the moment is not visible. Let us look at the updated layers dialog. Creating, selecting and editing layers has been made easier, and it is possible to have multiple layers created using the layers of commercial map services. For example, this land use layer. Let us now also make the MV network visible. If we look in this area, We see that the MV network layer is on top of the high voltage transmission network layer, but we would prefer this order to be reversed. In PowerFactory 2019, layer depth has been introduced, so it is easy to do this. On single line diagrams, there is now a new predefined layer called bays and sites, which is used with our new intelligent bay and site representation. These representations allow the user to move complete sites around rather than moving the individual network elements. Let's move one of the existing sites in order to have space for a new one. The new site can be created using the same site frame representation. A template is used to create the connecting elements, and the lines are connected. As you can see, the new elements are placed within the newly created site. Similar to sites, a smart representation of bay elements has been introduced. The elements within the bay can be moved as one, and elements added in the bay area will automatically be added to the bay. In this example, we will put a relay into the bay and connect a combined instrument transformer. To make things easier to see, I can turn the results boxes layer off using this new button. The order of a bay is used to indicate the real connection on a bus bar. Using a new option in the load flow command, the maximum current between all bus bar bays can be calculated and shown as Imax. For users working with protection devices, a new diagram plot type, the PQ diagram, is available, which shows the characteristic of the starting unit of a distance protection device in the PQ plane. Let us look at the relay here, which has an overcurrent starting unit. Here we can see the RX plot and the PQ plot of this relay. We see that it transforms into a circular characteristic. The voltage factor is used to set the minimum operating voltage for the power calculation. If we run a load flow, we see that the current operation point is inside the characteristic, so the protection device will not operate. This is useful for grid operators to identify the operation point of generation groups or power limits of transmission lines in order to avoid nuisance tripping. Of course, the other starting types, such as impedance starting, are also supported. If we change to impedance starting, we see that it is likewise transformed into the PQ plane, and again we can run the load flow to see whether the operation point lies within the area of the characteristic. There are a number of new and enhanced models available in PowerFactory 2019, and I would like to show you one example. For all transformer and reactor types, the saturation models for electromagnetic simulations have been greatly improved, making it possible to model the non-linear flux-current relationship of the iron core of such elements. Furthermore, the saturation curve can now be defined in PowerFactory based on RMS current voltage measurements, which are frequently provided by the manufacturer. The measurements of the voltage-current relationship are usually only executed up to a voltage of 1.2 per unit. However, for transformer and reactor energization, the magnetic flux relationship is also relevant for values above that level. Therefore, the user can, in addition, enter a saturated reactance. In version 2019, the user can also define the residual flux of the transformer in the element directly for each phase. This represents the remaining flux in the transformer after disconnection. We will now show the effect of the transformer saturation during energization. The transformer is energized at T equals 0 by closing the circuit breaker of all three phases. After closing the circuit breaker, the magnetic flux in the three phases exceeds 1 per unit, as shown here, and will drive the transformer into saturation. Due to the nonlinear flux-current relationship of the saturation curve, this will lead to high inrush currents, as shown here. The high inrush current will cause a voltage dip at the grid connection point, as shown in this last plot. In this version, we have also introduced a hysteresis model for transformers, which may have a significant impact on the inrush current of transformers, shunts, and series reactors. The history-independent hysteresis model is supported for all models with saturation. The hysteresis loop is based on the loop width defined by the user and the saturation curve. For this transformer type, a loop width of 1% is defined. The following simulation shows the magnetic flux current relationship for this transformer, including hysteresis. I have introduced you to some of the major developments in PowerFactory 2019, but the release contains many other new features, as well as new and enhanced power system models. Please refer to our What's New document for more information.